Ancient balls of stars hold secrets that defy the laws of physics. These are globular clusters, dense swarms of ancient suns orbiting the fringes of our galaxy. By the end of this journey, you will possess a radically new perspective on the cosmos. We will explore stars that appear older than the universe itself and question if dark matter is knotted within these stellar cities. What does it truly mean to look back in time? These ancient stellar cities present us with a paradox so profound it threatens to unravel our cosmic timeline. Inside the cluster known as M92, astronomers have found stars that seem to be older than the universe itself. The very idea sounds impossible, a logical contradiction that defies everything we think we know. How can something exist before time and space began? The answer lies in how we measure a star's birthday. Scientists use a method called main sequence turn-off point analysis. Think of the main sequence as the stable, adult phase of a star's life, where it burns hydrogen in its core. The turn-off point is the specific moment on a chart of a star cluster when the most massive stars begin to exhaust their fuel and leave this main sequence. It acts like a cosmic hourglass, telling us precisely when the sand started flowing for that entire family of stars. By identifying this point, we can date the entire cluster with remarkable precision. The calculations for clusters like M92 point to ages of around 13.8 billion years. But the universe, based on the rate of its expansion and the afterglow of the Big Bang, is calculated to be 13.8 billion years old. This creates a glaring impossibility. The stars cannot be the same age as the cosmos. They need time to form after the Big Bang cooled sufficiently. This leaves us with a stark choice, a cosmological crisis that forces us to question our most fundamental tools. Either our methods for dating stars are fundamentally flawed, missing some critical piece of physics that makes these ancient suns appear older than they are, or our understanding of the Big Bang and the universe's expansion is incomplete. Perhaps the universe is older than we think, or maybe something we have not yet discovered happened in those first fleeting moments after creation. This single observation turns these glittering star clusters from mere celestial ornaments into the keepers of our cosmos's deepest, most challenging secret. This stellar age crisis is not the only paradox hiding within these ancient cities. Look deeper into a cluster like NGC 6397, and you will find stars that simply should not be there. Amidst the ancient, cool red giants, you see brilliant, hot blue stars burning with a youthful intensity that defies all logic. Astronomers call them blue stragglers. They are the cosmic outliers, the rebellious stars that appear younger and bluer than every other star in their ancient neighborhood. According to everything we know about stellar evolution, all the stars in a globular cluster were born at roughly the same time from the same cloud of gas. The most massive stars should have lived fast, burned bright, and died long ago. So what are these vibrant blue stars doing in a retirement home for ancient suns? How do they cheat cosmic death? The leading theory is as dramatic as it sounds: stellar cannibalism. In the densely packed core of a globular cluster, stars are not distant, solitary beacons. They are a teeming metropolis where stellar close encounters are common. Sometimes two older, lower-mass stars collide in a violent merger. This cosmic car crash creates a single, more massive and hotter star, essentially hitting the reset button on its life. It gains a fresh supply of hydrogen fuel and begins burning brightly again, appearing young and blue amidst its ancient cousins. Another possibility is a slower, more intimate theft. Many stars exist in binary systems, two stars locked in a gravitational dance. If one star begins to swell into a red giant, its outer layers can be siphoned off by its greedy companion. This mass transfer rejuvenates the receiving star, making it more massive, hotter, and bluer. It is a stellar vampire stealing life from its partner to prolong its own. The Hubble Space Telescope has brought these theories to life, capturing stunning evidence within clusters. We can now observe these binary systems in the act of mass transfer and identify the merged stars by their unusual brightness and temperature. These blue stragglers are not just cosmic anomalies, they are active participants in a brutal, ongoing drama of collision and consumption. They prove that even in the oldest structures in the universe, the story of stellar life and death is still being violently rewritten. But the cosmic drama of stellar cannibalism is not the only secret these clusters have been keeping. For decades, the prevailing wisdom was simple. A globular cluster was a single, simple family of stars, all born together from one pristine cloud of primordial gas. They were thought to be the ultimate example of a single stellar population. Yet, when astronomers pointed their most powerful telescopes and spectrographs at these clusters, they uncovered a truth that was far more complex and fascinating. The stars were not all identical twins. They were more like cousins with different family histories, revealing a story of multiple generations living under the same roof. This discovery of multiple stellar populations shattered a long-held assumption. The key evidence came not from how bright the stars were, but from the precise chemical fingerprints of their light, a technique called spectroscopy. By breaking starlight into its constituent colors, scientists can identify the unique signatures of elements present in a star's atmosphere. When they did this for stars within the same cluster, they found a pattern that should not have been possible. Some stars showed the expected pristine composition, rich in hydrogen and helium with only trace amounts of heavier elements, but other stars in the very same cluster showed clear chemical enrichment. Their atmospheres were polluted with higher levels of helium, sodium, and nitrogen. This is a cosmic contradiction. How can stars born at the same time and from the same material have such different chemical identities? The answer points to a prolonged and dynamic formation history. The leading theory suggests that the first generation of stars to form in the cluster was massive and short-lived. These titanic stars burned through their fuel in only a few million years before exploding as supernova. These violent deaths flooded the cluster with newly forged heavy elements, enriching the remaining gas. Then, a second generation of stars began to form from this polluted material, carrying the chemical imprint of their ancestors. This later generation was born with that extra helium, sodium, and nitrogen baked right into them from the start. It means a globular cluster is not a single, instantaneous event. It is a cosmic recycling plant where the death of one generation directly fuels the birth of the next. This forces us to completely rethink the life cycle of these ancient structures. They were not quiet and peaceful retirement homes. They were vibrant, chaotic nurseries where star birth and star death were locked in a continuous, self-perpetuating cycle for millions of years. This chemical recycling leads to another profound silence, a cosmic crime scene with no evidence of the crime itself. Within these ancient stellar cities, we find countless white dwarfs, the dense, Earth-sized cores of dead stars. These are the faded remnants of stars that once lived and died, and many of those deaths should have been spectacular supernova explosions. Yet, when we search for the expanding clouds of debris, the glowing remnants that such explosions leave behind, we find nothing. No young supernova remnants exist in any globular cluster. It is a baffling absence, as if a forest filled with fallen, ancient trees showed no sign of any ever having crashed to the ground. So where did all the supernova go? The first clue lies in the nature of the explosions that created these white dwarfs. Not all stellar deaths are the same. The most massive stars end their lives in core collapse supernova, titanic blasts that leave behind neutron stars or black holes and create vast, glowing remnants that can persist for thousands of years. But the white dwarfs we see today come from a different, more gentle end. They are the ghosts of lower mass stars that shed their outer layers peacefully, leaving their cores to cool for eons. For a white dwarf to explode, it needs a trigger. This happens in a Type 1, a supernova, when a white dwarf in a binary system steals so much material from its companion that it crosses a critical mass threshold and detonates completely. This is a rare event, but in a cluster teeming with binary stars, we should still see the evidence, the glowing, expanding shells of gas from explosions that occurred in the last few thousand years. Their total absence points to a startling possibility. Perhaps the initial recipe for star formation in these clusters was fundamentally different. The initial mass function, the distribution of stellar sizes when the cluster was born, might have been skewed. It is possible that globular clusters simply never formed many of the most massive stars, the ones destined for violent core collapse supernova. They may have been factories for smaller, longer-lived stars from the very beginning. Another, more dynamic theory suggests that the environment itself cleans up the evidence with ruthless efficiency. A supernova explosion in the crowded core of a cluster would blast material outward at tremendous speeds. But in the dense gravitational field of the cluster, this ejected material might not be slowed down by surrounding interstellar gas because there is very little of it. Instead, the supernova ejector could be flung out of the cluster entirely, escaping its gravity and racing into the emptiness of intergalactic space. The remnant would dissipate so quickly and so completely that it would be invisible to our telescopes within just a few centuries, leaving no lasting trace for us to find. This creates an eerie picture of these glittering clusters. They may be sites of constant, silent violence, where stars explode and their ashes are instantly swept away into the cosmic void, leaving behind only the silent, glowing embers of white dwarfs as the only witnesses. This eerie silence of past supernova is broken by the rhythmic, rapid-fire ticking of cosmic clocks. Deep within the dense cores of clusters like Terzan 5 and 47 Tucani, astronomers have discovered a strange overabundance of millisecond pulsars. These are neutron stars, the incredibly dense, city-sized cores left behind after a supernova, spinning hundreds of times every single second and emitting powerful beams of radiation like a runaway lighthouse. Their presence in such numbers is another profound puzzle. A pulsar is a dying star's final act, a beacon born from collapse. But a normal pulsar spins slowly at first, and over millions of years it should lose energy, its rotation slowing to a crawl until its beams fade into silence. So how do these old neutron stars in ancient clusters become these hyperactive spinners? The answer is a cosmic resurrection, a process called recycling. In the crowded stellar metropolis of a globular cluster, a lone neutron star often finds a partner, locking into a gravitational dance with a normal star. If they are close enough, the intense gravity of the neutron star begins to steal material from its companion. This stream of gas does not just fall onto the neutron star, it slams into the surface with incredible force, transferring energy and, crucially, angular momentum. Think of it like a spinning ice skater. When a skater pulls their arms in, they spin faster. For the neutron star, this incoming gas acts like a continuous pull, a torrent of material that spins it up to impossible speeds. Over hundreds of millions of years, this process can accelerate a sluggish, elderly pulsar into a millisecond pulsar, the fastest spinning objects in the universe. The dense environment of the cluster is the perfect factory for this phenomenon. The sheer number of stellar encounters creates the binary pairs necessary for this mass transfer to begin. These recycled pulsars are more than just cosmic curiosities. They are extreme physics laboratories. Their incredible density and stability make them perfect for testing the laws of gravity and even for the ongoing hunt for gravitational waves. They are the resurrected dead spinning at the edge of possibility, all thanks to the violent intimacy of their stellar home. These resurrected pulsars are not the only invisible giants hiding in the stellar crowd. At the very heart of some of the most massive globular clusters, astronomers have found evidence of a different kind of dark resident, one that could rewrite the story of how black holes grow. For years, scientists have debated a tantalizing question: do these ancient clusters contain intermediate mass black holes? These would be cosmic missing links, far larger than the stellar mass black holes created by collapsing stars, yet vastly smaller than the supermassive monsters that lurk in galactic centers. Finding one would be a monumental discovery, and the hunt has focused on the cores of clusters like Omega Centauri. The search does not rely on seeing the black hole itself, for it is, by nature, invisible. Instead, scientists watch the stars dancing around it. By measuring the velocities of stars swirling in the cluster's dense core using powerful telescopes and spectrographs, astronomers can detect the irresistible pull of an unseen gravitational master. In Omega Centauri, the stars at the very center are moving at astonishing speeds, whipping around as if orbiting something incredibly massive and utterly dark. The only logical explanation for this frantic stellar dance is the presence of a black hole with a mass of tens of thousands of suns. Similar evidence has been found in other massive clusters, like G1 in the Andromeda Galaxy, where stellar motions also point to a central, dark anchor of immense proportions. This is the signature of an intermediate mass black hole, a gravitational titan holding court in the oldest neighborhood in the universe. The implications are staggering. If these black holes are real, they could be the primordial seeds from which the supermassive black holes at the centers of galaxies later grew. Perhaps these clusters were not just satellites of galaxies, but the original building blocks, their central black holes merging over cosmic time to form the giants we see today. Their existence suggests a hidden lineage, a secret family tree for the most powerful objects in the cosmos, with its roots buried deep within these ancient globular clusters. These clusters are not the isolated fortresses they appear to be. Surrounding some of them, like the ghostly Palomar 5, astronomers have found long, faint streams of stars stretching across the sky. These are tidal tails, the visible evidence of a cluster being slowly torn apart by the immense gravitational pull of our galaxy. Think of the Milky Way's gravity as a cosmic tide, and the globular cluster is like a ball of sand held just above the ocean surface. The side of the cluster closest to the galactic center feels a stronger pull than the side farther away. This difference in force, the tidal force, relentlessly stretches the cluster, pulling stars away from its main body. Over billions of years, this process strips the cluster of its stars, creating two long, flowing rivers of stars, one leading the cluster in its orbit and one trailing behind. These streams are incredibly faint and difficult to see, but they are not just cosmic wreckage. They are exquisite tools for an invisible kind of cartography. The path these stellar streams take as they orbit the galaxy is exquisitely sensitive to the distribution of mass, including the dark matter we cannot see. Dark matter forms a vast spherical halo around our galaxy, and its gravity guides the flow of these streams. By meticulously mapping the shape and structure of a tidal tail like the one from Palomar 5, scientists can trace the invisible scaffolding of the dark matter halo itself. Any kinks, gaps, or distortions in the stream are like fingerprints, revealing the presence of smaller clumps of dark matter that the stream has encountered on its long journey. This turns a dying cluster into a natural physics experiment, its disintegrating body charting the hidden geography of the cosmos. The silent cartography of tidal streams points toward an invisible presence, but the true nature of that darkness may be knotted even tighter to the clusters themselves. One of the most contentious debates in modern astronomy revolves around a simple question: do globular clusters contain their own dark matter? The classic view was that they do not. They were considered bare, with all their mass accounted for by the twinkling stars we can see. But this clean picture is being challenged by strange gravitational anomalies. The method is straightforward. You measure two different kinds of mass. The luminous mass is the total weight of all the stars, gas, and dust we can observe. The dynamical mass is calculated by observing how fast the stars are moving within the cluster. Just like planets orbit the Sun faster when they are closer to its strong gravity, stars on the outskirts of a cluster should move more slowly if the only gravity comes from the visible stars in the center. Yet, in several clusters, the stars are moving far too quickly. Their high velocities suggest the cluster contains much more mass than we can see, a classic signature of dark matter's gravitational grip. This would mean each cluster is not a bare island of stars, but is instead embedded within its own small, dense halo of invisible matter, a private knot of darkness it has carried since its birth. The implications would be revolutionary, suggesting these clusters formed within their own tiny dark matter cocoons in the early universe, fundamentally changing our understanding of their origin. But the story is not so simple. A powerful counter-argument has emerged, one rooted in the complex lives of the stars themselves. Skeptics point to the intricate stellar populations within clusters. Remember those multiple generations, the blue stragglers, the binary systems, and the legions of stellar remnants like white dwarfs and neutron stars. Advanced computer models now show that this complex mix can dramatically alter the internal gravity. As massive stars die and shed mass, or as stellar interactions fling lighter stars outward, the cluster's gravitational core can shift and evolve. The rapid stellar motions we measure might not be due to dark matter at all, but simply the lingering gravitational echo of countless stellar collisions, mass transfers, and explosive deaths that have churned the cluster over billions of years. The visible stars we see today may simply be tracing the ghostly gravitational potential carved out by their long-dead ancestors. This leaves us with a perfect scientific standoff. Is the missing mass a cloak of dark matter, a relic from the dawn of time? Or is it just the invisible weight of a violent history, the accumulated gravity of stellar ghosts? For now, the clusters hold this secret close, their true nature hanging in the balance between an ancient darkness and a more recent, but equally profound stellar chaos. The gravitational tug-of-war between dark matter and stellar chaos is not the only conflict within these ancient cities. Amidst the stellar cannibalism and resurrected pulsars, there exists a possibility that seems almost peaceful: the existence of planets. The very idea of a stable, orbiting world in such a violent, crowded environment defies belief. Yet the evidence, however tentative, points to just that. The most famous and surprising candidate was found not around a normal star, but in the cluster M4 orbiting a pulsar. This was not a world like Earth, basking in the warm light of a stable sun. This was a potential planet circling the corpse of a dead star, a cosmic zombie bathed in intense radiation. The discovery was made by detecting tiny, rhythmic variations in the pulsar's incredibly precise clock-like ticks. The planet's gravity caused a minuscule wobble in the pulsar's position, changing the arrival time of its pulses by mere milliseconds. This revealed a world with about 2.5 times the mass of Jupiter, on a wide orbit that takes about 100 Earth years to complete. Finding any planet here is astonishing, but finding one around a pulsar is a cosmic paradox of the highest order. A pulsar is born from the violent supernova death of a massive star, an explosion that should have utterly vaporized any pre-existing planets or blown them into the void. So how did this world survive, or how did it form in the aftermath of such total destruction? One theory is that it is a second-generation planet. The supernova may not have completely destroyed its original solar system. The blast could have stripped a gas giant down to its core, leaving behind a solid, rocky body that later re-accreted a new atmosphere from the debris. Another, more dramatic possibility is that the planet itself was born from the ashes. The supernova explosion and the subsequent formation of the pulsar created a rotating disk of metal-rich debris around the newborn neutron star. From this disk, a new world could have coalesced, a planet forged directly from the remains of a dead star. This would be a world with a truly unearthly composition, possibly made of diamond or other crystalline carbon structures, a glittering relic of stellar apocalypse. But the challenges do not end with its birth. The environment of a globular cluster is a hostile place for planet formation. The stars are so close together that the gravitational pull from a passing neighbor could easily rip a young planet from its orbit or fling it into the cold of interstellar space. Furthermore, the intense ultraviolet radiation from thousands of hot, young stars in the cluster's early days would have boiled away the protoplanetary disks of dust and gas, the very material from which planets are built before they had a chance to coalesce. This makes the potential planet in M4 a cosmic miracle, a testament to the stubborn persistence of worlds even in the most unlikely and violent corners of the universe. Its existence, if confirmed, suggests that planet formation is not just a feature of quiet, suburban stellar neighborhoods. It is a universal process that can persist against all odds, even in the chaotic, high-rise downtown of a globular cluster. Even the color of a star can reveal a hidden cosmic crime. Beyond the brilliant blue stragglers, astronomers have identified another class of stellar misfits, the yellow stragglers. These stars shine with a distinct golden yellow light, placing them in a strange no-man's land on the charts of stellar evolution. They are brighter and hotter than the ancient red giants, yet they are not part of the main sequence of normal hydrogen-burning stars. They are stellar outliers, glowing with a color that simply does not fit the aging population around them. Just like their blue cousins, their existence points to a violent and intimate past. The leading explanation is that they are the products of stellar mergers or dramatic mass transfer, but with a different outcome. Imagine two stars, both relatively low in mass, colliding and combining. The result is a single star with a new, intermediate mass. This new star is not massive enough to become a brilliant blue straggler, but it is more massive than any of the original, aging stars in its neighborhood. It settles into a new equilibrium, burning with a steady yellow intensity that marks it as different from everyone else. Alternatively, a yellow straggler could be born from a slower process. In a close binary system, one star might siphon off just the right amount of material from its companion. This stolen mass rejuvenates the star, extending its life and altering its temperature and luminosity to land in that peculiar yellow zone. It is a cosmic facelift, giving the star a second youth that manifests as this unusual golden glow. These yellow stragglers are more than just curiosities. They are living laboratories for studying the deepest interiors of stars. When two stars merge, their internal structures are violently scrambled. The resulting yellow straggler gives astronomers a unique chance to observe a stellar interior that has been literally turned inside out. By analyzing the light from these stars, scientists can probe the mixing of different elements and test theories about how stellar cores behave under such extreme conditions. The specific chemical signatures found in their atmospheres can tell the story of the merger itself, revealing which star donated more material and how thoroughly the two were mixed together. Each yellow straggler is a cosmic crime scene, and the light it emits is the forensic evidence telling a story of collision, theft, and rebirth written in the language of physics and chemistry. This helium enrichment is far more than a simple chemical footnote. It fundamentally rewrites the life story of a star. For a star born with an extra helping of helium in its core, everything changes. Helium is heavier than hydrogen, so a helium-rich core is denser and hotter from the very beginning. This forces the star to burn its nuclear fuel at a far more furious rate. The result is a star that lives its life in the fast lane, burning brighter and hotter than its pristine siblings, shining with a distinctive blue tint before aging along a completely different path. It is the cosmic equivalent of two people born on the same day, but one having a faster metabolism that changes their entire appearance and lifespan. This single discovery shattered the long-standing astronomical paradigm of the simple stellar population. we could no longer look at a globular cluster and see a single, cohesive family of stars that all aged gracefully together. Instead, we are looking at a divided society. The second generation, polluted with the ashes of their massive ancestors, lives a life of brilliant, frantic intensity. They are the hard-living members of the cluster, destined to burn out faster. The first generation, by comparison, are the slow and steady elders, conserving their pristine hydrogen fuel for a longer, more stable existence. This forces us to see the color and brightness of a cluster not as a uniform indicator of age, but as a complex tapestry woven from multiple, distinct life cycles. The brilliant blue light we see emanating from a cluster is no longer just from young stars. It is also from these older, helium-enriched stars masquerading as youth, their very composition forcing them to put on a brilliant, deceptive show. How many other cosmic assumptions are now being called into question by this fundamental division hidden within the light of these ancient cities? This chemical divide goes even deeper than helium, into the very elements that make up the stars themselves. When astronomers peer into the hearts of these clusters, they find a bizarre chemical trade-off happening among the lighter elements, a pattern that defies simple logic. In many stars, the levels of sodium and aluminum are curiously high, while at the same time, the amounts of oxygen and magnesium are strangely low. This is not a random fluctuation. It is a precise anti-correlation, an inverse relationship that acts like a cosmic fingerprint. Where one set of elements is abundant, the other is always scarce. This pattern is the smoking gun, pointing directly to a specific and violent polluting source from the cluster's deep past. These elements cannot be forged in the gentle nuclear fires of a typical, long-lived star. Their creation requires the extreme temperatures and pressures found only in the cores of truly massive stars. The process that creates this signature is known as hot hydrogen burning. Imagine the core of a giant star as a massive chemical factory. At temperatures exceeding 40 million degrees, the star begins fusing not just hydrogen into helium, but also heavier elements. In these intense conditions, a chain of nuclear reactions occurs. Neon atoms capture protons and transform into sodium. Magnesium atoms undergo the same process, turning into aluminum. But this factory has a limited supply of raw materials. To create this new sodium and aluminum, the star must consume the existing oxygen and magnesium in its core. It is a transformative process, a nuclear alchemy where one family of elements is systematically converted into another. When that massive, short-lived star ends its life in a supernova, it does not just explode. It scours its own interior, blasting this newly processed sodium and aluminum-rich material out into the surrounding cluster. This polluted gas, now depleted in oxygen and magnesium and enriched with the new elements, then mixes with the remaining pristine hydrogen and helium. When the next generation of stars forms from this contaminated raw material, they are born with this specific chemical imbalance already written into their light. They carry the evidence of their ancestors' violent deaths in their very atmospheres. This is how we find ancient stars that are simultaneously rich and poor, enhanced and depleted, all because they were built from the ashes of a cosmic forge that no longer exists. Size is a cosmic illusion when it comes to globular clusters. You would naturally assume that the most massive cluster, the one containing the greatest number of stars, would also stretch across the widest expanse of space. Yet, this is not what we observe in our own galactic backyard. The heavyweight champion of the Milky Way's clusters, Omega Centauri, is indeed immense, but its physical diameter is not the largest. That title belongs to other, less massive clusters, revealing a profound disconnect between a cluster's weight and its width. The true master of a cluster's dimensions is not its mass, but the relentless gravitational tug of war it has endured for eons. This is the great size mystery, and its solution lies in two opposing forces: the crushing gravity of the galaxy and the explosive energy of the stars within. Our galaxy's gravitational pull creates a powerful tidal field. Imagine the Milky Way as a giant, and a globular cluster is a ball of string held in its hand. The side of the cluster closest to the galactic center feels a much stronger pull than the far side. This difference in force, the tidal force, constantly tries to stretch the cluster and rip it apart. A cluster can only hold onto stars that are bound tightly by its own gravity, stars that can resist this external stretching. This creates a theoretical boundary, a tidal radius, beyond which stars are easily stripped away by the galaxy. A cluster that orbits very close to the galactic center experiences an intensely powerful tidal field, which compresses it, preventing it from expanding outward. It is kept on a short, tight leash. Its stars are packed into a dense, compact sphere simply to survive. On the other hand, a cluster with a wide, looping orbit far from the galactic center experiences a much weaker tidal force. This cluster lives on a long, loose leash. It has the freedom to expand, its stars spreading out over a much larger volume of space, even if the total number of stars is relatively small. So a less massive cluster with a distant orbit can appear much larger on the sky than a far heavier cluster that is forced to live in the crowded, violent inner city of the galaxy. But the galaxy's tides are only half the story. The internal dynamics of the cluster itself play an equally dramatic role. Over billions of years, a gravitational sorting process occurs within the cluster, a phenomenon known as mass segregation. The most massive stars and stellar remnants, like neutron stars and black holes, gradually sink toward the cluster's core through countless gravitational interactions. It is a cosmic settling process where the heaviest objects naturally drift to the center, while the lighter, lower mass stars are pushed out to the outskirts. This process releases a tremendous amount of gravitational potential energy, which acts like a heat source in the cluster's core. This energy can cause the entire cluster to expand, puffing up its outer layers. In some cases, this internal heating can even push stars beyond the tidal radius, where the galaxy's gravity promptly plucks them away, leading to the cluster's gradual evaporation. The final size of a globular cluster we see today is therefore a fossil record of its entire life, a delicate balance struck between the external pressure of the galaxy's tides and the internal heat generated by its own stellar population. A massive, compact cluster like Omega Centauri has likely survived by withstanding both the galaxy's pull and its own internal fireworks. A large, low-mass cluster may be in the final stages of its life, its loose structure a sign that it is being gently torn apart. The physical size of these ancient cities tells us not just about their present, but about their long and violent history of survival against impossible odds. This gravitational sorting creates a strange void in the cluster's heart, a missing population of its smallest citizens. If you could take a census of a globular cluster's core, you would find it curiously deficient in small, faint, red dwarf stars. These low-mass stars should be the most common inhabitants, outnumbering all the giants and blue stragglers, yet their numbers in the central regions are surprisingly thin. This is not an error in our observations. It is the direct result of a relentless physical process called dynamical friction, a cosmic game of gravitational billiards playing out over billions of years. In the crowded confines of a cluster, every star is constantly pulling on every other star. When a massive star moves through a sea of lighter stars, its strong gravitational field acts like a wake, disturbing the paths of the smaller stars around it. The lighter stars tend to clump together slightly behind the massive star, and their collective gravitational pull acts as a drag, slowing the heavy star down. It is like a giant wading through a crowd of children, the constant little tugs and bumps gradually robbing him of his momentum. This dynamical friction steadily bleeds energy from the most massive stars, causing them to spiral inward, sinking slowly and inexorably toward the cluster's center. Meanwhile, the opposite happens to the low-mass stars. In these gravitational interactions, energy must be conserved. As the heavy stars lose energy and fall inward, the lightweight stars gain that energy, getting a gravitational kick that pushes them into higher, wider orbits at the cluster's outskirts. Over eons, this process systematically sifts the cluster's population, concentrating the stellar heavyweights neutron stars, black holes, and giant stars in a dense central core, while the common red dwarfs are banished to the fringes. But for the very smallest stars, the outcome is even more dramatic. Some receive such a powerful gravitational kick that they are flung completely out of the cluster, ejected at speeds greater than the cluster's escape velocity. They become cosmic orphans, rogue stars drifting forever in the dark halo of the galaxy, invisible testaments to the violent gravitational shuffling within their former home. What appears to be a missing population is actually an exiled one, a direct consequence of the relentless physics that governs life in a dense stellar city. The gravitational shuffling that exiles red dwarfs creates a crowded dance floor at the cluster's core, a place where stellar partnerships are not just common, they are the rule. Within the dense stellar soup of a globular cluster, binary star systems exist in a staggering bonanza, far outnumbering the solitary suns we are familiar with in our galactic neighborhood. This is not a quiet celestial community. It is a bustling metropolis where most stars live in pairs or even triple systems, locked in intimate gravitational embraces. This incredible frequency is a direct product of the environment. In the cluster's early days, stars were born so close together that gravitational capture was almost inevitable. As stars drifted past one another, their mutual pull could easily bind them together, forming binary systems that would last for billions of years. These are not just casual friendships, they are the primary engines driving the cluster's entire dynamical evolution. Every close encounter between a binary system and a single star is a complex gravitational negotiation. The interloper can be slingshot away at high speed, receiving a kick of energy that pushes it toward the cluster's outskirts. Alternatively, the single star can steal one of the binary partners, swapping places in a cosmic partner trade that reshuffles the stellar relationships. These frequent, chaotic interactions act like a central heating system for the cluster, pumping energy into the stellar population and preventing the core from collapsing in on itself under its own immense gravity. But the influence of these binary systems goes far beyond mere crowd control. They are the fundamental factories for the cluster's most exotic and dramatic inhabitants. The brilliant blue stragglers, those seemingly youthful stars in an ancient neighborhood, are almost exclusively born within these binary partnerships. They are the product of stellar cannibalism, where one star strips material from its companion, or the result of a direct collision and merger, creating a new, hotter, and more massive star. Similarly, the millisecond pulsars, those hyper-spinning neutron stars, owe their impossible speed to a binary companion. The pulsar acts as a cosmic vampire, siphoning gas from its partner star. This incoming stream of material carries angular momentum, spinning the pulsar up to hundreds of revolutions per second, resurrecting it from a slow, fading pulse into a rapid-fire cosmic lighthouse. Without this constant mass transfer from a binary partner, such incredible speeds would be impossible. Every exotic object we find in these clusters, from the reborn blue stars to the resurrected dead, points back to the same source, the relentless, dynamic, and creative power of the binary star bonanza. Even the predictable life cycle of a star holds hidden secrets when viewed through the chemical lens of a globular cluster. For decades, astronomers have used a powerful chart called the color magnitude diagram to map stellar evolution, plotting a star's color against its brightness. This creates a predictable path, a well-trodden highway that stars follow as they age. One of the most prominent stretches of this road is the red giant branch, where stars like our own sun will one day ascend as they expand into bloated, cool giants. But in globular clusters, this branch is not a smooth, clean line. It is marred by subtle kinks and bumps, tiny deviations that should not exist if all the stars were identical. These are the red giant branch anomalies, and they are the direct fingerprints of the cluster's divided chemical society. The specific way a star ascends this giant branch is exquisitely sensitive to the chemical composition of its deep interior. A star enriched with extra helium, a legacy of its second-generation birth, behaves differently than a pristine first-generation star. Helium changes the opacity of the stellar material, how easily light can escape from the core. This alters the star's internal structure and how it burns hydrogen in a shell around its core. The result is a star that climbs the red giant branch on a slightly different path, creating a bifurcation, a splitting of the single highway into two parallel lanes. One lane is for the pristine stars, the other for the polluted ones, but the anomalies go even deeper, revealing processes we can never directly observe. As a red giant ages, its convective envelope, the churning outer layer, can dive deep into the star, plunging toward the hydrogen-burning shell. This phenomenon, called deep mixing, acts like a massive dredge, pulling up material from the star's interior and bringing it to the surface. The material brought up is the nuclear ash from the hydrogen-burning process, rich in helium and nitrogen and depleted in carbon and oxygen. When astronomers analyze the light from these giant stars, they see the evidence of this dredge up clear as day. The surface of the star becomes chemically polluted with the interior's waste products. The specific kinks in the red giant branch correspond directly to the depth and efficiency of this mixing. A pronounced bump on the branch might indicate a moment when the convective envelope finally reached and ingested a specific layer of chemical discontinuity deep within the star. So, these seemingly minor wiggles on an astronomer's chart are not mere statistical noise. They are a live broadcast from the heart of a dying star, a detailed readout of its internal chemical factory and the deep, churning currents that are fundamentally reshaping it from the inside out. The very identity of the most massive globular clusters is now in question. We have long admired giants like Omega Centauri and M54 as the ultimate examples of these ancient stellar cities, but a radical theory suggests we have been misreading their cosmic resume. They may not be true globular clusters at all. Instead, they could be the ghostly hearts of long-dead dwarf galaxies, the surviving nuclei left behind after a violent act of galactic cannibalism. The evidence for this shocking transformation begins with their sheer scale and internal complexity. A normal globular cluster, for all its wonders, is a relatively simple structure. Omega Centauri, by contrast, is an anarchic metropolis. It contains millions of stars and, as we have seen, multiple distinct stellar populations with a wide range of metallicities, a term astronomers use for the abundance of elements heavier than helium. This spread in chemical composition is a galactic signature. A true globular cluster forms in a single, rapid collapse of gas, leading to a very narrow range of metallicities. A dwarf galaxy, however, forms stars over a much longer period, allowing supernova to progressively enrich the gas, creating stars with a much broader chemical palette. Omega Centauri possesses exactly this kind of complex chemical fingerprint, more like a miniature galaxy than a simple cluster. Then there is the case of M54. This massive cluster is not even orbiting the Milky Way on its own. It sits squarely at the center of the Sagittarius dwarf elliptical galaxy, a small satellite galaxy currently being torn apart and consumed by our own Milky Way. This gives us a front-row seat to the entire process. Astronomers believe that as the Sagittarius galaxy is completely stripped of its outer stars by our galaxy's gravity, M54 will be all that remains. It will be left as a free-floating, massive cluster, a trophy from a devoured galaxy. The final piece of evidence lies in their extended structures. These massive objects often show faint halos of stars or even their own tiny systems of satellite clusters, stretching far beyond the tight sphere of a typical globular. These are the ghostly limbs of their former galactic bodies, a faint echo of the larger structure they once commanded. this reclassification changes everything. It means the Milky Way's collection of globular clusters is not a pure family. It is a cosmic graveyard filled with both true clusters and the immortal hearts of galaxies we consumed long ago. These objects are not just clusters, they are survivors, the last kings of fallen kingdoms. This dramatic birth process contained the seeds of its own destruction. The very first generation of stars, the titans that forged the heavy elements, sealed the fate of their entire cosmic city. After their brilliant, short lives, they did not fade quietly. The most massive among them exploded as supernova, while others blew off their outer layers in fierce, relentless stellar winds. These were not gentle breezes, but hypersonic gales of radiation and hot gas streaming outward at millions of miles per hour. This created a cosmic hurricane that swept through the cluster with unimaginable force. The remaining hydrogen gas, the raw material for future generations of stars, was caught in this blast. It was heated to extreme temperatures and then violently expelled, pushed out by the tremendous pressure and lost to the void of intergalactic space. The cluster's own gravity, strong enough to hold stars, was not powerful enough to hold onto this superheated gas. In a relatively short time, perhaps only a few 100 million years, the cluster was rendered sterile. It was left a barren island of stars with no remaining fuel for new births. This event, known as quenching, is why every globular cluster we see today is an ancient relic. It is a fossil frozen in time, its star formation abruptly and permanently switched off over 10 billion years ago. Why did this happen so universally? The answer lies in the cluster's initial conditions. They formed with such a high density of massive stars that the resulting feedback was simply too powerful to withstand. The very violence of their creation guaranteed they would never create new stars again. Their stellar nurseries were not just closed, they were utterly annihilated by the firstborn generation. This leaves us with a profound thought. These glittering clusters are not just old, they are cosmic dead ends, their brilliant histories cut short by the cataclysmic fury of their own youth. The heart of a globular cluster is a place of immense gravitational tension, where the motions of stars betray a hidden and complex reality. We might assume that the very center of these dense stellar cities is a region of pure chaos, with stars whipping around at their fastest possible speeds. Yet observations reveal a different story, one with strange and unexpected quiet. Astronomers measure something called velocity dispersion, which is essentially the spread in the speeds of stars moving in different directions. In the crowded core, where gravity should be strongest, we often find less velocity dispersion than our models predict. The stellar dance floor is not as frenzied as we thought it should be. This kinematic anomaly is a profound clue, suggesting that the core is not governed by simple, predictable rules. One compelling explanation is that some clusters have already experienced a core collapse. This is a gravitational runaway process where so many stars have sunk to the center that the core becomes unstable. It contracts under its own weight, pulling stars into an ever tighter, denser knot. In the final stages of this collapse, the core can literally bounce back, a reaction driven by energy transfer from newly formed binary stars. This process can leave behind a surprisingly relaxed central region, a calm eye in the gravitational storm where the stellar velocities have settled into a new, unexpected equilibrium. These kinematics are not just abstract measurements, they are the primary tool in the hunt for the most elusive objects of all, intermediate mass black holes. The presence of such a dark giant would leave an unmistakable fingerprint on the motions of nearby stars. Imagine a handful of stars orbiting an invisible point, their speeds increasing dramatically the closer they get to that central nothingness. By meticulously mapping the velocities of stars in the core, astronomers can detect this gravitational signature, the frantic whirling that points to an unseen anchor with the mass of thousands of suns. This is how the search proceeds, not by looking for light, but by reading the subtle, silent language of motion written in the paths of ancient stars. The strange quiet at the heart of some clusters may not be a sign of simplicity, but the profound silence that follows a deep gravitational collapse, or the calm that exists in the shadow of a sleeping giant. The predictable path of stellar evolution begins to fray at the edges in these ancient clusters, revealing a strange new kind of star. On the standard color magnitude diagram, there is a stage after the red giant branch known as the horizontal branch. This is where stars settle after a dramatic helium flash in their core, and for a simple stellar population, it should appear as a tight, compact line of stars all burning at roughly the same temperature and brightness. But in many globular clusters, this line is not compact at all. It is stretched and pulled, forming an extended horizontal branch with stars scattered towards both hotter blue and cooler red extremes. This is not a random scattering, it is a direct and visible consequence of the cluster's secret chemical divide. The key factor is helium. A star born with a higher abundance of helium in its core has a fundamentally different internal structure from the very beginning. Its core is denser and hotter, leading to a more violent and efficient helium flash. When this helium-rich star finally sheds its outer layers and arrives on the horizontal branch, it does so with a much smaller, hotter, and denser core. This smaller size means it has a smaller surface area from which to radiate its intense energy. All that power concentrated into a tiny point makes the star blaze with a hotter, bluer light. It becomes a blue horizontal branch star. Meanwhile, a star from the pristine first generation with a normal, lower helium content will follow the expected path. After its helium flash, it settles onto the horizontal branch as a more typical, cooler, redder star. The extended horizontal branch is therefore a cosmic family portrait, showing us both the polluted and pristine stars side by side in a new phase of life. The spread from red to blue is not a sign of different ages, but a direct map of their different birth compositions. The helium-rich stars are literally too hot for their own good, forced into a brilliant blue existence by the ashes of their ancestors. This phenomenon creates a stunning visual diversity, but it also has a dramatic impact on the cluster's future. Those blazing blue horizontal branch stars are pouring out immense amounts of ultraviolet radiation, flooding the cluster with energetic light that we cannot see with our eyes but can detect with space telescopes. This invisible ultraviolet glow is a telltale sign of a cluster's deep chemical complexity, a hidden energy output driven entirely by the legacy of its violent first generation. The extended branch is more than a curiosity, it is a live display of stellar destiny written in the language of helium. Even the lightest elements hold cosmic secrets we are only beginning to decipher. Within the ancient atmospheres of globular cluster stars, astronomers have detected a baffling shortage of lithium. This simple element, the third lightest in the universe, is conspicuously absent, appearing in far lower quantities than our fundamental models of creation predict. This is the lithium problem, and it strikes at the heart of our understanding of the Big Bang itself. According to the theory of Big Bang nucleosynthesis, the first few minutes of the universe forged specific, trace amounts of the lightest elements hydrogen, helium, and lithium. This process left a predictable fingerprint, a primordial recipe that should be present in the oldest stars. When we look at ancient stars outside of clusters, we often find that expected amount of lithium preserved in their atmospheres, like a fossil from the dawn of time. But inside globular clusters, that fossil is broken. The lithium is missing. This creates a direct contradiction. How can the oldest stars in the universe, which should be pristine time capsules, lack an element that was one of the very first to form? The answer cannot be that the Big Bang produced less lithium than we thought because we see it elsewhere. The problem must lie within the stars themselves or within the unique environment of the cluster. It appears some internal stellar process is actively destroying lithium, and this process is dramatically enhanced within the crowded stellar cities. The leading suspect is a journey deep into the star itself. A star's atmosphere is typically a stable layer, but in these old, giant stars, a phenomenon called deep mixing can occur. Convective currents, like massive ocean currents within the star, plunge from the surface down toward the intensely hot core. As this material travels inward, it crosses a threshold where temperatures soar to over 2.5 million degrees. At that point, lithium, a fragile element, is destroyed through nuclear reactions. It is essentially burned as fuel. In a normal, isolated star, this process might be limited. But in a globular cluster star, particularly one born from that second, polluted generation with extra helium, the internal structure is different. The altered composition may facilitate more efficient and deeper mixing, dragging atmospheric lithium down to the furnace repeatedly over billions of years, systematically wiping it from the stellar record. Another possibility involves the cumulative effect of the cluster environment itself. The gentle but persistent tug of gravity from passing stars could subtly alter a star's rotation or internal dynamics over eons, stirring its interior in a way that amplifies this lithium-destroying process. The missing lithium is more than a chemical curiosity, it is a profound clue. It tells us that the environments within these ancient clusters do not just preserve stars, they actively transform them from the inside out, erasing the very signatures of creation we once thought were permanent. The predictable path of stellar evolution can be violently rewritten in a single, explosive moment. At the very faintest, bluest tip of the extended horizontal branch, astronomers have discovered stars that seem to defy all logic, so extreme they have earned the name blue hook stars. These are not merely hot stars, they are stellar infernos, burning at temperatures that dwarf even the blue horizontal branch stars. Their position on the chart is bizarre, appearing both incredibly hot and surprisingly dim, a combination that should be impossible for a normal, stable star. They are the ultimate cosmic outliers, and their existence points to a cataclysm that occurs at the very brink of stellar death. The leading hypothesis for their creation is as dramatic as it is precise, a last-second resurrection known as a late helium flash. Picture a star that has successfully ended its life. It has ascended the red giant branch, exhausted the helium in its core, and has begun its final journey, peacefully shedding its outer layers to become a white dwarf. It is already on the white dwarf cooling curve, settling into a quiet eternity as a fading ember. But for some stars, the story is not over. Deep within its shrinking core, a final, desperate ignition can occur. Just before the core becomes completely degenerate and inert, the remaining helium reaches a critical temperature and pressure. In a sudden, violent convulsion, the entire core reignites in a runaway helium fusion explosion. This is not the gentle helium flash of a typical red giant. It is a far more violent event because it happens in a much denser, more compact core. The star, which was moments from death, is blasted back to life. This late helium flash does not just restart the star, it fundamentally transforms it. The explosion blows away any remaining hydrogen envelope, leaving the star as a bare, intensely hot helium-burning core. This explains its strange position on the chart. It is incredibly hot because its fusion furnace is exposed, and it is faint because it is tiny, a shrunken, naked core shining with a furious blue-white light. This is a star that has cheated death not by stealing mass, but by surviving its own internal detonation. The blue hook stars are therefore cosmic phoenixes, stellar ghosts that burst back into a brilliant, final blaze just as they were fading into darkness. Their discovery tells us that even the most well-defined journey, the very textbook of stellar evolution, can be torn up and rewritten in a final, spectacular act of defiance. These ancient stellar cities exist in a state of profound and permanent silence. Unlike the vibrant spiral arms of our galaxy, filled with the glowing pink nebulae that are stellar nurseries. A globular cluster is a sterile environment, a museum where the exhibits are all impossibly old. If you were to fly through one, you would find almost none of the gas and dust that serves as the raw material for new stars. This remarkable cleanliness is a defining feature, and it forces us to ask a simple question. Where did all the material go? The answer lies in the cluster's long, punishing journey around the galaxy. Imagine a globular cluster orbiting through the galactic halo, a vast, thin soup of hot, ionized gas. As the cluster moves at tremendous speed, it plows through this material. The experience is like sticking your hand out of a car window at highway speeds, feeling the immense pressure of the air pushing against you. For the cluster, this is ram pressure. The thin galactic gas acts as a relentless wind, and it is far more effective than you might think. Any tiny amount of cool gas or dust that might still be lingering within the cluster from its early days is met with this hurricane-force torrent. The pressure is so intense that it simply scours the cluster clean, stripping away the residual material and sweeping it out into the void. But ram pressure is not the only janitor at work. The cluster itself is filled with sources of intense energy that heat and evaporate any potential star-forming fuel. Thousands of hot, blue stars and the furious ultraviolet radiation from the horizontal branch stars we discussed earlier flood the interior of the cluster. This radiation bombards any hydrogen atoms that might be present, heating them to extreme temperatures and giving them enough energy to escape the cluster's weak gravitational pull. Furthermore, the countless stellar winds from giant stars and the occasional shockwave from a nova explosion provide continuous internal pressure that pushes material outward, helping to empty the cluster from the inside. This combination of external stripping and internal expulsion is brutally efficient. It ensures that a globular cluster, once it loses its initial gas, can never again gather the resources to build a new star. They are cosmic dead ends, their brilliant futures stolen by the very environment they call home. This permanent sterility is why every star you see in a globular cluster is ancient, a fossil from a single, frantic burst of creation that was abruptly switched off over 10 billion years ago. This stellar color code is not as universal as we once hoped. Astronomers long assumed that a star's ultimate fate was written in one primary ingredient, its metal content. Yet the cosmos presents us with a glaring contradiction. We find two globular clusters, each with the exact same amount of heavy elements, but their horizontal branches look nothing alike. In one cluster, the branch is short and red, dominated by cooler stars. In the other, it is long and blue, stretched toward extreme heat. This is the second parameter problem, a decades-long puzzle that challenges our most basic understanding of stellar aging. If metal content is the first and most important parameter, what is the second factor that so dramatically reshapes a star's final act? The hunt for this hidden variable has uncovered several compelling suspects, each with its own compelling evidence. The first candidate is age. A slightly younger cluster might have a different distribution of stellar masses on the horizontal branch, potentially leading to a bluer appearance. But the age differences required are often too small to explain the dramatic variations we observe, leaving scientists searching for a more powerful influence. A far stronger suspect is helium, the very element we now know divides these clusters into distinct populations. A small boost in helium abundance can radically alter a star's core, making it smaller, hotter, and bluer when it reaches the horizontal branch. A cluster with a larger proportion of helium-enriched stars would naturally display a much more extended blue horizontal branch, solving the mystery. Yet helium alone may not be the sole culprit. The environment itself may be the second parameter. A cluster's density plays a crucial role. In a densely packed core, frequent stellar encounters and the formation of binary systems can strip stars of their outer hydrogen envelopes prematurely. Imagine a star being gravitationally bullied. its fluffy outer layers torn away to expose its hot, blue helium-burning core long before it would naturally shed them. This creates a blue horizontal branch star not through chemistry but through violence. The final suspect adds a new spin, quite literally. Stellar rotation, the speed at which a star spins, can fundamentally change its internal structure and longevity. A fast-rotating star mixes its fuel more efficiently, burning differently and potentially arriving on the horizontal branch with a different temperature and luminosity than its slower spinning twin. In the end, the second parameter may not be a single key, but a complex lock requiring several to open. It could be a combination of helium enrichment, dynamical history, and rotational velocity that together write the final chapter for these ancient suns. This means the color of a cluster's horizontal branch is not a simple metric, but a detailed autobiography, recording its unique blend of chemistry, crowd density, and spin. The ancient heart of a globular cluster is a place of perpetual motion, a cosmic contradiction where the oldest stars in the universe engage in a frantic dance that defies their age. While the stars themselves are ancient fossils, the gravitational environment they create is anything but static. It is a system in constant dynamic flux, capable of cycles of violent collapse and rejuvenation that keep the core eternally young. This is the paradox of dynamical youth, a process that prevents these stellar cities from becoming the silent, frozen graveyards we might expect. The most dramatic manifestation of this is a phenomenon known as core collapse. Imagine the cluster's core as a crowded room where everyone is slowly sinking toward the center. Over billions of years, through countless gravitational interactions, the most massive stars and stellar remnants lose energy and drift inward. This process, called mass segregation, causes the core to contract under its own ever-increasing weight. The density soars to impossible levels, with stars packed so tightly that the night sky from a hypothetical planet there would be a perpetual blinding daylight. If this process continued unchecked, the core would collapse into an infinitely dense point, but it never does. Just as the core nears its most extreme density, a rescuing force emerges from the chaos, the very binary star systems that the crowded environment created. These tightly bound pairs act as the cluster's gravitational energy source. When a single star has a close encounter with a binary system, the complex three-body interaction often results in the single star being slingshot away at high speed. This ejection is not a gentle process. It robs the binary system of some of its orbital energy, which is transferred to the escaping star as kinetic energy. This transfer acts like a central heating system, pumping energy back into the core and halting the collapse. In some clusters, this process can even cause the core to bounce back, expanding once more. It is a self-regulating cycle, a cosmic heartbeat where gravitational collapse is naturally countered by the energy output of its own stellar inhabitants. This means the cluster's core is not a fossil, but a living, breathing engine, where the relentless dynamism of its stellar population guarantees its own survival against the slow creep of gravitational death. The chemistry of these ancient stars can deceive us with its cosmic forgeries. Among the ancient metal-poor populations of certain globular clusters, astronomers have found stars that glow with a deep, ruby-red light, their atmospheres inexplicably rich in carbon. These are carbon stars, a discovery that defies all expectations, for they are cosmic imposters in a retirement home for the elderly. Carbon stars are typically associated with much younger, metal-rich environments where complex chemistry is the norm. Finding them in these ancient, pristine clusters is like discovering a modern skyscraper in the ruins of a prehistoric settlement. It simply should not be possible under the standard rules of stellar evolution. So how did these carbon-rich stars come to exist in a place where the building blocks for such complexity were thought to be absent? The answer lies not in their birth, but in a dramatic transformation during their old age. The leading theory points to a process of intimate stellar theft within a binary system. picture two elderly stars locked in a gravitational embrace. One star, as it ages and swells into a red giant, begins to churn its internal nuclear furnace. Deep in its core, a process called helium burning creates carbon as a byproduct. Normally, this carbon remains locked in the star's core, but in a close binary system, the intense gravitational pull of the companion star can act as a cosmic siphon. It pulls the carbon-rich material from the deep layers of the giant star, dredging it up to the surface and then stealing it away. The receiving star then becomes polluted with this imported carbon, its atmosphere now artificially enriched to appear as a carbon star. This is not a natural birthright, but a chemical makeover delivered by a stellar companion. Another possibility is an internal stellar rebellion. In some lone red giants, a phenomenon known as a deep mixing event can occur. Convective currents, like massive plumes, can dive from the star's surface deep into its interior, reaching the layer where helium is fusing into carbon. These currents then drag the newly forged carbon up to the stellar surface, effectively turning the star inside out. What was once hidden in the core is now displayed in the atmosphere, creating a carbon star through a violent act of internal upheaval. The discovery of these carbon stars forces us to see stellar chemistry not as a fixed identity, but as a dynamic and sometimes deceptive process. It proves that even the oldest stars in the universe are not finished products, but can be chemically reshaped by their companions or by their own turbulent interiors, leaving behind a false signature of youth in the most ancient of places. The predictable rhythm of variable stars can be found far from the city limits of their ancient homes. Astronomers have discovered a population of pulsating stars, like the reliable Lyrae variables, shining in the emptiness far beyond a globular cluster's traditional tidal radius. This is the boundary where the cluster's gravity should no longer be strong enough to hold onto its stellar citizens, yet here they are, beating like distant cosmic heartbeats in the dark. These are the extra-tidal variables, the escaped members of the cluster, and their existence tells a story of gravitational struggle that we can now read in their light. Each Lyrae star is a perfect standard candle, its intrinsic brightness known from its precise pulse. By measuring how bright it appears from Earth, we can calculate its exact distance with remarkable accuracy. When we find these stars strung out in long, faint streams, their positions and distances reveal that they are not random wanderers. They are tracing the precise path of their parent cluster's orbit around the galaxy, like breadcrumbs left behind on a cosmic trail. These escapees did not leave voluntarily. They were violently evicted by the relentless gravitational tides of the Milky Way. As the cluster orbits, the difference in gravitational pull between the side closest to the galactic center and the side farthest away constantly stretches and distorts it. Stars on the very edge, those just barely held by the cluster's weak grip, are the most vulnerable. A close encounter with another star within the cluster, or the gentle nudge from a passing molecular cloud, can provide just enough of a kick to push them over the edge. Once beyond the tidal radius, the galaxy's pull takes over, plucking them from their family and setting them adrift, but they do not drift randomly. Their motion is still dictated by the combined gravity of the cluster they left and the galaxy they now orbit. This makes them perfect tracers for mapping the cluster's extended gravitational field, a halo of influence that reaches far beyond the visible sphere of stars. By plotting the positions and velocities of these extra-tidal variables, astronomers can essentially perform an autopsy on the gravitational forces at play. They can measure the total mass of the cluster, including any hidden dark matter, and understand how the galaxy's tidal forces are slowly, inexorably, dissolving the cluster over billions of years. These lonely variable stars are more than just escapees. They are the ghostly periphery of the cluster itself, a faint echo of its structure that allows us to see the invisible hands of gravity at work. These ancient clusters might be the original architects of our galaxy. Their final and perhaps most profound mystery is not just what they are, but what they represent in the grand cosmic story. We have seen them as stellar cities, as chemical factories, and as gravitational puzzles, but they may hold an even greater title: the foundational building blocks of the galactic halo. The evidence for this is written in their very being. Their extreme age places their birth in the universe's chaotic first billion years, a time when the cosmos was a vast, dark canvas awaiting its first structures. Their orbits are a crucial clue, as many swing far out on wide, looping paths that carry them through the galaxy's sparse, spherical halo. They are not confined to the flat disk where younger stars like our Sun reside. They are ancient wanderers of a much larger, invisible territory. Their chemical composition seals the argument. The fact that the oldest clusters are so metal-poor, meaning they contain only trace amounts of elements heavier than helium, is a direct signature of their primordial origin. They formed from gas that had been scarcely touched by the nuclear furnaces of earlier stars, from a time before the universe had been widely seeded with the elements that make up planets and life. This combination of ancient age, halo orbits, and pristine chemistry paints a compelling picture of cosmic construction. In the early universe, vast clouds of dark matter began to collapse, pulling in the primordial hydrogen and helium gas. Within these collapsing clouds, the first globular clusters were born, blazing into existence as the first major stellar structures. As time progressed, gravity worked on a grander scale. These early clusters, along with smaller dwarf galaxies, were drawn together by their mutual attraction. They merged, their stars mixing to form the vast, diffuse halo that now surrounds galaxies like our Milky Way. The globular clusters we see today are the sturdy survivors of that epic era of assembly, the few that avoided complete disruption during these violent mergers. They are the immortal shards of the galaxy's infancy. This means that when you look at a globular cluster, you are not just looking at a dense ball of stars. You are looking at a fossilized piece of the galactic construction kit, a relic from a time when the universe was building its largest structures from the smallest, brightest pieces. They are the enduring foundation stones upon which the majestic spiral of our galaxy was ultimately built. Their story is a testament to the fact that our universe is far stranger and more dynamic than we ever dreamed. What we once dismissed as simple, serene stellar retirement homes are in reality cosmic paradoxes, places where the laws of physics are stretched to their limits and the narrative of cosmic history is constantly rewritten. These ancient cities are not mere ornaments. They are fundamental keys for unlocking the secrets of stellar evolution, galaxy formation, and the universe's deepest past. From stellar cannibals and resurrected pulsars to the potential hearts of devoured galaxies and the ghostly pull of dark matter, every mystery solved within them seems to reveal two more, driving astronomical research forward into bold new territories. They stand as a permanent reminder that in the vast library of the cosmos, the oldest books often contain the most surprising and revolutionary stories. The final chapter on these cosmic paradoxes has yet to be written, for our tools of discovery are about to become unimaginably powerful. The next generation of observatories, like the James Webb Space Telescope and the Vera C. Rubin Observatory, are poised to turn our deepest questions into tangible data. With Webb's piercing infrared vision, we will peer through the dense veils of dust at the hearts of clusters, seeking the unambiguous gravitational signature of an intermediate mass black hole. We will watch the stellar waltz in the core with a precision never before possible, looking for that telltale frantic whirling that confirms a dark titan's presence. Simultaneously, the Vera C. Rubin Observatory will conduct a relentless, decade-long survey of the entire sky. Its vast eye will monitor thousands of clusters night after night, catching the subtle flickers and movements that betray rare events. It could witness the sudden flare of a stellar merger creating a blue straggler, or map the faintest outer streams of disintegrating clusters with unprecedented detail. giving us a new and powerful map of the dark matter halo that guides them. These instruments will not just test existing theories, they will undoubtedly reveal phenomena we have not even begun to conceive. Will we find a new, unknown class of hypervelocity objects flung from cluster cores? Could we detect the faint thermal glow of planets orbiting pulsars, worlds forged from stellar ash? The very nature of dark matter's role, whether it is a primordial cloak or the ghostly weight of stellar history, may finally be settled by the sheer weight of this new evidence. These ancient stellar cities have kept their secrets for over 13 billion years, but their walls are about to come down. The light they have been holding back is now waiting for our new eyes to see.